In this section, we're going to be continuing to talk about logarithms. We're going to talk about the properties of logarithms. We have two objectives. We want to convert logarithms of products, powers, and quotients to expressions in terms of individual logarithms and conversely, and B, simplify expressions of the form type log base a of a to the x and a to the log base a of x. So, at the top of our handout, we have a summary of some logarithmic properties, but before we go into depth on this, we're going to make some comparisons to some things that we already know. So let's go ahead and start with the product rule for exponents. So we have the product rule for exponents. If we multiply two things together that have the same base, so a to the m times a to the n, this is equal to a to the m plus n. It turns out that with logarithms, we get something very, very similar. So one of the key things we want to remember is that logarithms are exponents. And we'll notice that in this, the logarithms do what the exponents do. So if we're multiplying two things together with the same base, we're going to add the logarithms because the logarithms behave as if they are exponents. Similarly, we have a quotient rule for exponents. And our quotient rule for exponents says if we have a to the m divided by a to the n, then this is a to the m minus n. And if we look at our handout once again, we have our quotient rule, which says if I have the logarithm base a of m divided by n, then it is the same as the difference of the two logarithms. So if we divide two things with the same base, we subtract their exponents. The next rule we want to talk about is the power of a power rule. And our power of a power rule says if I have a to the m raised to the nth power, then this is the same as a to the m times a to the n. So if we look at our corresponding logarithmic property, we get the following. If I have the logarithm base a of m raised to the p power, then that is the same as p times the logarithm base a of m. So each of our logarithmic properties corresponds to an exponential property. And remember that logarithms are exponents. So the logarithms are going to do whatever it is the exponents do. Alright, so let's take a look at example number 1. So express as the sum of logarithms. So for this one, we're going to need to use our product rule. So we have that the logarithm of m times n is equal to log m plus log n, where our base doesn't change. So in our example, our m is going to be 5, and our n is going to be x, and our base in this one is going to be c. So the logarithm base c of 5x is going to be the same as the logarithm base c of 5 plus the logarithm base c of x. So when we use this property, notice that the base of our logarithm stays the same. All right, it's now your turn. So before I turn you loose to work on this example, how many times are we going to need to use the product rule? Well, we have 1, 2, 3 factors, so we're going to end up with 3 logarithms. And we're going to get the natural logarithm of x plus the natural logarithm of y plus the natural logarithm of z by using the product rule twice. All right, let's take a look at our next example. In this next example, we're going to need to start off by using the quotient rule. So let's go ahead and identify our numerator, and the quotient rule is going to be xy, and the denominator is going to be z. So that's going to give us the logarithm base c of xy minus the logarithm base c of z. And after using our quotient rule on this first term, we're going to need to use our product rule. Similar to what we did in the previous example, then, we're going to get a logarithm base c of x plus a logarithm base c of y minus a logarithm base c of z. All right, it's now your turn. Let's go ahead and have you guys do you try number 2. So once again, we're going to need to start by using the quotient rule. So we're going to get the logarithm of x minus the natural logarithm of y times z. And similar to what just happened in the previous problem, we're going to have to use the product rule once again. And that's going to give us the natural logarithm of x minus, and then using the product rule, we're going to have the natural logarithm of y plus the natural logarithm of z. So then distributing that minus sign into our parentheses, we get the natural logarithm of x minus the natural logarithm of y minus the natural logarithm of z. So we have to be just a little bit careful with parentheses and grouping when working on these types of problems. All right, let's take a look at our next example. Example 3, we wish to express the logarithm of x to the 7th power as a product. So this time we're going to use the power of a power rule, or our power rule for logarithms. So using our power rule, we're going to get 7 times the logarithm of x. And if we want to think of it this way, the 7 just swings down around in front. All right, it's now your turn. Let's go ahead and have you guys work this problem. So once again, we're going to take our exponent, and we're going to swing it down in front so we get 1/2 times the natural logarithm of x. All right. So just as a reminder, we want to talk about our fractional exponent rule. Well, our fractional exponent rule says that the square root of x is the same as x to the 1/2 power. This has a couple of things that we need to remember. So on a square root, even if we don't write it, the index is 2, and on our variable on the inside, even though we don't write it, the exponent is 1. So in general, we have the following. If we have x raised to the a divided by b, this is going to be the same as the bth root of x raised to the a power. So in the example we just had, our index was 2 and our exponent was 1, so we got 1/2. So for example, if I had the 5th root of x to the 3rd power, this would be x raised to the 3/5. All right. So now that we're equipped with that, let's go ahead and have you guys take a look at try number 4. So before I turn you loose, there are several different ways that we can do this. So if you remember when you first learned about your exponent rules, as long as you don't break any rules, there is more than one way to get to the correct answer. The same thing is true for our logarithmic properties. There is more than one way to get to the correct answer, and sometimes that method will involve a mixture of both exponent rules and logarithmic properties. So let's go ahead and get started. So let's go ahead and simplify this expression just a little bit. So I have log base a of x to the 6th over p to the 5th and q to the 8th. Using the quotient property of radicals, this is the same as the square root of x to the 6th over the square root of p to the 5th times the square root of q to the 8th. So then we can use our fractional exponent rule. So that's going to give us the logarithm base a of x to the 6/2 divided by p to the 5/2 and q to the 8/2. And that's our fractional exponent law. And then we just simplify that up a bit. And we have the logarithm base a, 6/2 gives us 3. 5/2 doesn't simplify, and there's a typo there. The answer is 4. It's 8/2 gives us q to the 4th power. So then, the next thing we would use is the quotient property of logarithms. And the quotient property of logarithms gives us the logarithm base a of x cubed minus the logarithm base a of p to the 5/2 q to the 4th. And then on this next piece right here, we're going to use our product property of logarithms. And that gives me the logarithm base a of x cubed minus the logarithm base a of p to the 5/2 plus logarithm base a of q to the 4th. Distributing into our parentheses, we get logarithm base a of x cubed minus the logarithm base a of p to the 5/2 minus the logarithm base a of q to the 4th power. And then finally, by the power rule, we bring all of our exponents out in front, and we get 3 times logarithm base a of x minus 5/2 logarithm base a of p minus 4 times logarithm base a of q. All right, let's take a look at our next example. Example 4, express as a single logarithm. So once again, there are multiple ways that we can do this. So the first thing that we could notice is that these are like terms. So then that's 1/2 or 1/3 plus 3 take away 2. So one over 3 plus 3 take away 2 gives me 4/3. So then I would have 4 over 3 natural logarithm of x. And that would express this as one logarithm. And if I wanted to now, I could use my product rule backwards. So that would be the natural logarithm of 4/3, which would be the natural logarithm of the cube root of x to the 4th. Method 2, which is a little bit longer, if we use our power rule, again in reverse, we would get the natural logarithm of x to the 1/3 plus the natural logarithm of x cubed minus the natural logarithm of x squared. Then on these first two pieces, we could use our product rule. So then that's going to give us the natural logarithm of x to the 1/3 times x cubed. So then we would have 1/3 plus 3 using our exponent rules. So that would give us the natural logarithm of x to the 10/3 minus the natural logarithm of x squared. Then on these two pieces, we would use the quotient rule, which says that we're going to divide. So we would have the natural logarithm of x to the 10/3 all over x squared. But if we divide two things with the same base, we subtract their exponents. So 10/3 take away 2 gives us the natural logarithm of x to the 4/3. And we'll notice after all of that, oh, that's exactly the same as what we had here. So notice we got the same answer, but one of these methods was a bit longer than the other. All right, the next example is for you guys. So go ahead and let's give you try number 5 a go. So first thing we notice, once again, we have subtraction, so let's go ahead and use our quotient rule. So that gives us the logarithm of x squared minus 5x take away 14 all over x squared take away 4. And then we factor each of these. So factors of negative 14 that give us negative 5, well, 14 has factors 7 and 2, so that's negative 7 and positive 2. And then we have the difference of squares, so that's x minus 2 over x plus 2. Our x plus 2's reduce out. And we get, after all of that, the log of x minus 7 all over x minus 2.